Chapter 14 is more about chance and probability. First, we're going to do a few more examples on how we can find probabilities. So one of the ways that we can figure out our chances is by listing all of the ways that an event can happen and then counting or adding up our individual chances. So for example, if a woman gives birth to quadruplets, then what's the probability that she has 2 boys and 2 girls? Assuming that male and female births are equally likely and that the gender of the babies are independent. Now, gender of the babies being independent just means that the first baby doesn't affect the gender of the next baby, and so forth. So what we could do is we could list out all of the possible combinations. So for example, you could have boy, 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 boy. Or you could have girl, 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 girl. Boy, girl, girl, girl. Girl, boy, girl, girl, etc. And if we're logical about it and we have a systematic way, we can list out all of the possible outcomes. So now we want to find the probability that she has 2 boys and 2 girls. So we're looking for the probability of 2 boys and 2 girls. So what I can do is just come through and look at all of the outcomes that have 2 boys and 2 girls. So this one has 2 boys and 2 girls, as does this one, this one, this one, this one, and this one. I think those are all of our options that have 2 boys and 2 girls. So there are 6 outcomes that have what we're interested in of 2 boys and 2 girls out of a total of 16 total. And so we have 6 out of 16, or I could change that to a decimal of 0.375. So once again, I listed out all of my possible outcomes and then just figured out which outcomes had the I was interested in. So for our next example, let's say that we want to draw 2 tickets at random with replacement from this box. So this box has the tickets 2, 3, 4, and 4. We're going to draw 1 ticket out, look at it, put it back, and then draw another ticket. So what are all the possible outcomes? So to save us time, I've listed out all the possible outcomes. So you can get a 2 and a 2, or 2 and a 3, 2 and a 4, etc. So number 1, what is the chance that the tickets show the same number? So what I'm going to do is just look at it and see which outcomes have a ticket with the same number. So it's 2 and 2, 3, 3, 4, 4, 4, 4, 4, 4, 4, 4. I believe that's it. So there are 6 out of a total of 16. So my final answer is 16. For my next one, what is the chance that the first number is smaller than the second number? So again, just go through, circle all the outcomes that have the first number that's smaller than the second number. So it's 2, 3, 2, 4, 2, 4, 3, 4, 3, 4. It looks like those are my only possibilities. So there are 5 out of a total of 16. And number 3, what is the chance that the sum of the numbers is odd? So I have to go through and look at the sum. So 2 plus 2, that would be 4, that's even. But 2 and 3 would be 5, 3 and 2, 3 and 4, 3 and 4, 4 and 3, 4 and 3. I think those are all of the possible outcomes that give us a sum that is odd. And there are 1, 2, 3, 4, 5, 6. So 6 out of 16. In our next example, we're going to talk about the game Monopoly. So a player who rolls doubles, the same outcome on both dice, gets a second turn. So what is going to be the probability of rolling doubles? Once again, we just go through and say, okay, where do we get doubles? So 1 and a 1, 2 and a 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So there are the probability of doubles is that there are 6 possible ways to get doubles out of a total of, if I count all of those up, there are 36. My answer is 6 out of 36. Now in our next example, in the game Settlers of Catan, you roll 2 dice and you look at the sum. So I made for you a table of the possible values of the sum of the 2 dice. So for the first dice you can get 1, 2, 3, 4, 5, or 6. Second dice, same thing. And then on the inside I put all of the sums. So number 1, again, I've listed all of the sums for you. What is the chance that the sum is 7? So you just have to say, okay, how many 7s are there? There are 1, 2, 3, 4, 5, 6 7s. So the probability of a 7 is that there are 6 of a total of 36 options. Let's see. let's come over to number 3. What is the chance that the sum is odd? So that would be the 3s, 5s, 7s, 9s, and 11s. Now I need to count up how many that is. So that if I count it up, there are 18 of them. So the probability of it being odd, that something odd, is that there are 18 out of 36. Or if you want, you could simplify that to 1/2 or 0.5. Let's see, number 2, what is the chance that the sum is 6 or the sum is 8? So we're interested in all of the 6's. We're also interested in all of the 8's. So let's count up how many that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of a 6 or 8 is that there are 10 out of a total of 36. And number 4, what is the chance that the sum is either even or odd? This one I don't actually have to calculate anything, but because the sum has to be either even or odd, there are no other choices, so the chance that it's either even or odd is 100%. Because numbers have to be even or odd. There is no other choice. Specifically, whole numbers, which sums are. So the whole numbers have to be either even or odd. There's no other choice. So the sum has to be even or odd. The probability is 100%. Next, mutually exclusive. So two outcomes are mutually exclusive if the occurrence of one prevents the occurrence of the other. Or in other words, if one happens, the other cannot. So they cannot happen together. So the following are examples of mutually exclusive events. So first, a student takes stats at 10:30 on Tuesdays and Thursdays, and the same student takes engineering at 10:30 Tuesdays and Thursdays. That would be mutually exclusive because you can't take two different classes at the same time. Or a baby is a boy and then the same baby is a girl. You have to be either a boy or a girl. And then a fair coin toss results in heads, or the same toss results in tails. A coin toss has to land in either heads or tails. It can't be both at the same time. So for our next example, which of the following are mutually exclusive? So number 1, drawing cards from a 52 card deck, getting a heart and getting a queen. Okay, are those mutually exclusive? Can they happen at the same time? So this is not mutually exclusive because queens can be hearts. And hearts can be queens back and forth, so they can happen at the same time. Number 2, drawing cards from a 52 card deck, getting a heart and getting a black. So can the same card be both a heart and a black? No, so these are mutually exclusive because hearts are always red. They cannot be black. And so those two events would be mutually exclusive. They can never happen at the same time. Number 3, roll a die and get a 6 and an odd number on one die roll. Can that happen at the same time? No, a 6 is even, so you can't get the 6 and have it be an odd number, so it can't happen at the same time. So you can't get a 6 and an odd on the same roll. They cannot happen at the same time. Number 4, roll a die, get a 6 and an even number. Well, a 6 is an even number, so if you roll a 6, you get a 6 and an even number, so they can happen at the same time. So this would be not mutually exclusive, because 6 is an even number, so they can happen at the same time. Now that we've learned about mutually exclusive, we have what's called the addition rule. So if two events are mutually exclusive, meaning that they cannot happen at the same time, then the chance that one happens or the other happens is equal to the sum of the two chances. But if they're not mutually exclusive, the sum is going to be too big. Okay, so we can only do this rule if we know that they're mutually exclusive, so they can't happen at the same time. So for example 123, choose a card from the deck. What is the chance that the card is a heart or a spade? So first ask yourself, can you get a heart or a spade at the same time? No, those are two different suits. They can't happen at the same time, so these are mutually exclusive. So if I want the probability of a heart or a spade, it's going to be equal to the probability of a heart plus the probability of a spade. Now I just need to know those probabilities. Okay, if you're confused about this, go back and look at chapter 13 where I have the diagram of everything that's in a deck of cards. So how many hearts are in a deck? In a deck there are 13 hearts out of a total of 52 cards. Plus, now I want spades. There are 13 spades out of a total of 52. Now, if you wanted to, if you think about it as the probability of a heart is 1/4, 13 out of 52 does simplify to 1/4. You might have done 1/4 plus 1/4. You'll get the same answer. So this would be 26 out of 52, or 1/2. Example 124, draw one card from a well-shuffled deck. What is the chance that you draw a jack, a queen, or a king? So first of all, this is mutually exclusive. You can only get one of those outcomes at a time. There are no cards that have a jack, a queen, and a king on the same card, so they don't happen at the same time. So we're looking for the probability of a jack, or a queen, or a king. And when we see ors, we're going to add the probabilities. So this is the probability of a jack, plus the probability of a queen, plus the probability of a king. So probability of a jack, there are 4 jacks out of a total of 52 cards. There are 4 queens out of a total of 52 cards. And there are 4 kings out of a total of 52 cards. So this gives me 12 out of 52. If you were using your calculator, then your calculator is going to simplify this for you automatically to 3 out of 13. Example 125, let's toss 2 coins, so these are 2 separate coins. What is the chance that you get exactly 1 head? So to get exactly 1 head, you have to ask yourself, well, what are the ways that I can get exactly 1 head? First of all, what are all the possible outcomes? Let's do that first. So all possible outcomes is that you could have head-head, or head-tail, or tail-head, or tail-tail. And we're only interested in the outcomes that give you exactly 1 head. So if you want to get exactly 1 head, you're looking for the probability of head tails or tails heads. And when you have the or, you can add the probabilities. So this is the probability that you get a heads and then a tails, plus the probability that you get a tails and then a head. And what do we do when we see the word and? We multiply. So the probability of heads and then tails, probability of heads is 1/2. Now times it by the probability of tails, which is 1/2. Plus, now the probability of tails is 1/2. And the probability of heads is 1/2, and we're going to multiply. So this gives me 1/4 plus 1/4. So my final answer is 1/2. So there's a 1/2 chance that we get exactly one head. And finally, what is the difference between mutually exclusive and independent? This is something that usually confuses students every semester. So mutually exclusive and independence are two completely different ideas. They don't have anything to do with each other. Two completely different ideas. So two events are mutually exclusive when one event can't happen if the other event already happened. So they can't happen at the same time. Next, two events are independent when knowing that one event already happened doesn't change the chance of the other event occurring. Or in other words, they don't affect each other. So let's go through in our next example, and for each example we're going to talk about whether these events would be mutually exclusive or not. Remember, mutually exclusive means can they happen at the same time. So in a family of 4 children, getting exactly 2 boys and getting exactly 3 girls. That can't happen at the same time because then you would have 5 children. So this would be mutually exclusive. Next, let's toss 3 coins. And we want to get heads, 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 and tails, tails, tails. Can you get that at the same time? Well, no. So if you have heads, 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 you can't also have tails, tails, tails. So this would be mutually exclusive. Number 3, tossing 3 coins and getting head, 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 and also, can you get at least 1 head? Well, yes, because head, 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 that has 2 heads, so that's at least 1 head. So this is not mutually exclusive, because they can happen together. Number 4, look at a deck of cards. The top card is an ace, and the bottom card is an ace. Well, I see no reason that the top card can't be an ace and the bottom card be an ace, so this would be not mutually exclusive. It's possible for both to happen together. Let's see, 2 more. Rolling a die and getting a 1 on the first roll and getting a 1 on the second roll. Okay, is there any reason that you can't get a 1 on the first roll and a 1 on the second roll? I don't see any reason for that, so these would be not mutually exclusive. And number 6, look at a deck of cards. The top card is a king of spades, and the bottom card is a king of spades. Okay, is that possible for both of them to happen at the same time? No. Not possible for both to be king of spades because there is only 1 king of spades in the entire deck, so it can't be on the top and bottom at the same time. So this would be mutually exclusive. Now for example 127, we're going to identify for each set of events whether it's independent or dependent. Remember, independent or dependent means whether or not they affect each other. So number 1, roll a die twice, getting a 1 on the first roll and getting a 1 on the second roll. So if you get a 1 on the first roll, does that affect whether or not you get a 1 on the second roll? No, they don't affect each other. So this would be independent. Number 2, look at a deck of cards. The top card is an ace and the bottom card is an ace. Okay, so now this one is slightly interesting. So if I tell you that the top card is an ace, let's see, does the probability of the bottom card being an ace change? Okay, so what do you think? If you already know that the top card is an ace, does that mean that the probability of the bottom card being an ace changes? Yes, because there are less aces to choose from. So this one would be not independent, which means that it is dependent. Number 3, look through a deck of cards. The top card is red and the top card is hearts. So if I tell you the top card is red, does the probability of the top card being hearts change? What do you think? So yes, normally probability of hearts is 1/4, but if you know the card is red, then the probability of hearts is now suddenly 1/2, because half of the red cards are hearts. So this is an example of where the two probabilities or events affect each other, or the probability changes. So this is not independent, or in other words, it is dependent. If it's not independent, then it is dependent. So number 4, look at the weather, and it is cloudy and it is raining. So in other words, if I tell you that it is cloudy, does that change the chance of it raining? Yes, more likely to rain if sky is cloudy. So they affect each other, so they are dependent. Now the next thing we're going to talk about, something else that always confuses people, is when do you add and when do you multiply? So you add the chances when you want the probability that A or B happens. Now keep in mind, this only works if A and B are mutually exclusive. And then you multiply the chances when you want the probability that A and B both happen together. Now don't forget on this one, we do have to use the conditional probabilities unless you know that A and B are independent. So let's just make ourselves the note up at the top. So OR means add, and means multiply. For now, we're going to put this into play and practice. So example 128, a deck of cards is shuffled. You're interested in the top and bottom cards of the deck. Find the chances if you can. So number 1, the probability that the top card is the king of spades or the bottom card is the king of spades. Now keep in mind, the top card can't be the king of spades and the bottom card be the king of spades at the same time. These are mutually exclusive because they can't happen at the same time. And that's good because that means if they're mutually exclusive, then we can add their chances to find the probability of the OR. So the probability that the top is king of spades or the bottom is king of spades means we just have to add the two probabilities. So the probability that the top is king of spades is 1 out of 52. Plus, and the probability that the bottom is king of spades is 1 out of 52. So the chance that either the top or the bottom is king of spades is 2 out of 52. Now number 2, the chance that the top card is king of spades and the bottom card is king of spades. So normally I would multiply here, but I don't even have to do that because what is the probability that the top is the king of spades and the bottom is the king of spades? That would be 0 because it's impossible for both of them to be king of spades at the same time. That's why they were mutually exclusive. Number 3, the chance that the top card is an ace or the bottom card is an ace. Okay, and so if I started doing this without paying a lot of attention, I would say, okay, this is the probability. The top is an ace or bottom is the ace, and I say, okay, so that would be the probability of the top ace plus the probability of the bottom ace. But what is wrong with this? What am I doing wrong? You can't do that. You can only add the probabilities if they're mutually exclusive. Or you're in another stats class and we learn more complicated rules for when they're not mutually exclusive. But in this class we only do the very basic rule, and so we just say we can't find this. So these are not mutually exclusive because you can have the top card be an ace and the bottom card be an ace at the same time because there's 4 different aces. So not mutually exclusive because they can happen at the same time since there's 4 aces in deck. So you can't find this probability because you can't add the probabilities. Number 4. What is the chance that the top card is an ace and the bottom card is an ace? So probability of top ace and bottom ace. Well, for an n, we just have to multiply. So top ace times the probability of a bottom ace. Let's see, so the probability of getting a top ace, there are 4 aces out of a total of 52 cards. But now, if you know that the top card is an ace, how many aces are left? There are only 3 aces left to choose from for the bottom, out of a total of 51 cards. So you have to be careful there. Notice these are conditional probabilities because my probability changed based on my first card. So if my top card is an ace, now there's only 3 out of 51 cards left for the bottom. So this gives me 12 out of 2,652. And then this example actually goes back to an example we did in chapter 13, where I told you we were dealing with the red marbles and yellow marbles, and there was something I told you that people tend to have problems with, and we were going to prove it later on once we got to a point that we could. And that's now. So I have a box with 2 red marbles and 3 yellow ones. And we want to reach in and choose 2 marbles without replacement, so we don't put the marble back. So A, the thing that people had trouble believing is, what is the chance that the second marble is red? So if you don't know anything about the first marble, the chance that the second marble is red is still 2 out of 5. And people had a hard time believing that because they said, well, we already pulled 1 marble out and we didn't put it back, so shouldn't the probability change? It doesn't, okay, and the reason why is that you don't know anything about the first marble. Now let's actually prove it. So we're going to fill in the table for each of the possible outcomes and probabilities for drawing the 2 marbles. So when you draw your marble, you could get, say, a red and a red, or a red and then yellow, and you could get a yellow and then red, or you could get yellow and yellow. So if I was to find these probabilities, so the probability of getting a red and a red, probability of getting the first red would be 2 out of 5. Then I want to get another red, so there's only 1 red out of a total of 4. So this would be 2 out of 20. Then if I want to get a red and then a yellow, so there's 2 out of 5 marbles that are red. Now I want to get a yellow, so there's 3 yellow marbles to choose from out of a total of 4. So this would be 6 out of 20. And then for yellow and red, there are 3 yellows to choose from, and 2 reds, but only a total of 4 marbles because I already pulled 1 out. So this would be 6 out of 20. And then if I want yellow and yellow, there are 3 yellows to choose from the first time. But if I pull one marble out and I don't put it back, now there's only 2 yellows out of a total of 4. So this would be 6 out of 20. Now just to double check, if I add all these up, so 2 plus 6 plus 6 plus 6, that does give me 20 out of 20. So all of my chances add up to 1. All of your chances should always add up to 1. And now, if we are interested in the chance that the second marble is red, to find the probability that the second marble is red, we just add up the probabilities for each of the possible outcomes that have the second marble as red, which would basically be this one and this one. So the probability that the second marble is red is equal to the probability that you get red, red, or yellow, red. And so we just have to add up each of those probabilities. So if I add up each of those probabilities, probability of red, red would be 2 out of 20. Probability of yellow, red is 6 out of 20. When I add this up, I get 8 out of 20. If I divide the top and bottom by 4, that does give me 2 out of 5. And so you can see that we proved that even though we are drawing our marbles without replacement, if you don't know anything about the first marble, then the chance of the second marble is red is going to be just our unconditional probability of 2/5, or kind of our original probability. Now let's see if that also happens when we choose 2 marbles with replacement. So with replacement, the chance that the second marble is red is still just 2 out of 5. Sounds a little easier to believe, but let's go ahead and find all the probabilities just kind of for practice. So if we want the probability of red and red, or we could do red, yellow, or yellow, red, or yellow, yellow. The chance of getting a red and then a red, well, the chance of getting our first red would be 2 out of 5 times for the end, and now I want to get another red marble, but I put my first marble back, so now the probability of getting a red is still 2 out of 5. So this will be 4 out of 25. And then for red and then yellow, there are 2 out of 5 red marbles, and then we put our marble back, and now we want to get a yellow. There are 3 out of 5 yellow marbles, because again we put our first marble back. So 6 out of 25. For yellow red, there are 3 out of 5 yellows, and then 2 out of 5 reds. Again, we multiply because we want the yellow and red. So this is 6 out of 25. And for yellow, yellow, it'd be 3 out of 5 times 3 out of 5, which gives me 9 out of 25. Double check. Yes, if I add up all my probabilities, they do add up to 1. Okay, now add the probabilities for each of the possible outcomes that have a red marble for the second draw. So the probability of second marble is red. To get that, we just say, well, what's the probability of red, red, or yellow, red? So that's the probability of red, red, plus the probability of yellow, red. So red, red is 4 out of 25. Yellow, red is 6 out of 25. And if we add those together, we do get 10 out of 25, or 2/5. And that's why our probability of getting the second marble being red is still 2/5.